Hello everyone and welcome back to Techmine Guru. I am your coach Supratim. Today we are diving into DSA lecture 25. We will be exploring QuickSort and Comparators, delving into the art of order and custom rules. So here is our roadmap for today. We will start with the pivot partition, which will act like our engine. Then we will look at QuickSort itself, which will serve as the vehicle. After that, we will cover comparators, which will provide the customization over the vehicle. And finally, we will look at an application of sorting by rules. So let's begin with the pivot partition. So you have been given an array. You have to consider the first or the last element as the pivot, and you have to rearrange the array so that all elements which are lesser than the pivot are on the left side of the array, and which are greater than equal to pivot are on the right side. So suppose this array has been given 54, 26, 93, 17, 77, 31, 44, and 56. So if you take the first element as a pivot, which is 54, so how many elements are lesser than the pivot element? 26, 17, 31, 44, right? Similarly, how many elements are greater than 54? 93, 77, and 55. So all these elements which are lesser than the pivot element will be on the left side of the array, and all the elements which are greater than the pivot element will be on the right side of the array. So you have to rearrange the array like this. So let's understand that with the code. So let's see the code for the same along with a dry run. So the code is very simple. So suppose you are taking the first element as the pivot. So you have defined pivot is equal to a of 0. So here we will take two pointers, I and j. So you have taken the leftmost element, I is equal to L, and you are running a for loop from j is equal to L to r minus 1. That is from the leftmost element to the rightmost element. And when your j pointer will move, you have to check whether it is smaller than the pivot element. If it is smaller than the pivot element, we will simply swap that particular jth element with the ith element, and we will increase the I pointer. So two pointers will be there, I and j. J will iterate over the loop, and every time the element pointed by the j is lesser than pivot element, we will swipe that element with the element pointed out by the I pointer. And once this is done, we will swap that ith element with our pivot element. So let's understand this code with a dry run. So let's keep pivot as 10, right? And what will be I? I will be equal to 0. And since j will also start from 0 to length of the array. So what will be the length of the array? It will be 8, right? So the j will run from 0 to 7. So we will check here if a of 0 is lesser than the pivot or not. Since a of 0 is the same number, we will not swap it. Next, the j pointer will move to 13. We will check whether 13 is lesser than 10 or not. So this condition will not work. So we will not swap. Next, we will again move to the next element 7. This time 7 is lesser than the pivot element. So as soon as we got an element lesser than the pivot element, we will swap the element pointed out by the I pointer and the j pointer. So we will swipe 7 here and 10 at this place. Similarly, then we will move to the next element 8, and that time our I will increase to I++, which will become 13 now. Now j will be at 8, right? So it will check now 8 is lesser than 10 or not. So 8 is also lesser than 10. So we will again swipe 8 with the element present in the ith pointer. So where is the I pointing now? 13, right? So 8 will come here and 13 will come here. Now again our j pointer will increase. It will reach to 25. Now since I++ will happen after swap, so I will point to this element now, which is currently now 10, and our j will point to 25 now. Now it will again check whether a of j, which is 25, is lesser than pivot element or not, and the pivot element was 10 only, right? So it will say this condition will not work. So again j will increase to 20. Now it will check again whether 20 is lesser than the pivot element or not. It will say no. So again swapping will not happen, and the j will come to the next element, which is 23. Now again it will check whether 23 is lesser than 10 or not. It will again say false, and again j will come to this last position. Now it will check whether a of j is lesser than the pivot or not. It will say yes, and it will swap the element present in the ith pointer with the jth pointer. So right now where is I pointing? It is pointing at this element, which is 10. So j will come to this position. So 5 will come to this position, and 10 will go to last position. And now I will come to the next element, since I++ will happen. And at last we will come out of the for loop, and we will swipe the element pointed by the I pointer with the pivot element. So 13 will go this side and 10 will come to the pivot point. And what is the index where pivot element is present, it will be 4. So it will return the pivot index where the pivot element actually should lie. So if you see the result in the left array, 7, 8, 5 will come, then after that 10 will come, and in the right array it will be 13, 25, 20 and 23. So we will see in the QuickSort how we apply the same. But in QuickSort, the process is, it will involve recursive partitioning the left and the right subarrays until the size is 1. So you have to apply this above partition concept in the left and right subarrays until the size becomes 1 here. So we have to apply recursion here. So this is the base condition of our QuickSort. If L is greater than equal to R, it will return from the recursive function. Now it will do a partition, it will get the pivot element, and once we get the pivot element, we will recursively sort the left subarray from L to one element lesser than the pivot element, and similarly we will recursively solve the right array using the next element of the pivot element to R. So left subarray will run from L to pivot element -1, and right subarray will run from pivot element +1 to R. So as you remember in the merge sort, we were sending in the recursive function L to mid -1, right? And for the right subarray, we were sending from mid +1 to R. Similarly, instead of that mid, we got a pivot element from this partition function, and which simply have the rule that the elements, and we already saw how this partition functions work. So in this, we have selected the rightmost element as the pivot element, and we have simply used that two-pointer technique using I and j to get the pivot index. So this pivot index will tell that all the elements present in the array which are lesser than the pivot have come to the left side of the array, and all the elements present in the array which are greater than the pivot element will come to the right side of the array. So if you see the recursion tree here, so every time your function will start with length n, and since they are being divided into left and right subarray, so this will get reduced. So our array length will get reduced, and it will reach till we get the size of the array as 1, or till we hit this base condition. So this will be like log n levels, right? And inside each function, if you see the time complexity of this partition function, so we are running one for loop only, that is from L to R -1. So the time complexity here is O of n. And since on every function call, this is getting divided into 2 halves, and we have log n levels, so our total time complexity will be O of n log n. And since we are not taking any extra space like we were using in merge sort, in which we were taking 2 auxiliary left array and a right array, that's why our space complexity in that case was O of n. But in this, we are not taking any extra space other than this pivot element, so the space complexity will be O of 1 only. And for complete QuickSort, since we are using log n level of recursive stack, so the total space complexity will be O of log n. But let's see the best and average case in case of QuickSort. So in best and average case, the time complexity of QuickSort will be O of n log n, and the space complexity is O of log n. But in the worst condition, suppose if the array is reverse sorted, in that time our time complexity will be O of n square, and our space complexity will be O of n, because it will have a deep recursive stack in case of reverse sorted array. So how to fix the worst condition and bring the complexity down to O of n log n? So for this, we use some approach called randomized QuickSort. So in this, we will choose random pivot. So how to choose a random pivot? So we will get a random integer from L to R using some random library used in our language, and then we will initially swap A of R with that A of random index, and then once that swapping is done, we will again take the pivot element as A of R, and then we will normally run the partition with A of R as a pivot element. So you can think why this randomization works. So let's understand that with the math. So suppose you have been given n elements, and you have to choose a random element which can be the maximum in that n elements. So what is the probability of choosing a random element so that it becomes a maximum? It will be 1 by n, right? So you have to keep choosing this random element consecutively, right? Because this partition function will get called from each left and right subarray in the recursive QuickSort, right? So when you choose the maximum element from given n elements, the first time when you choose, it will be 1 by n, right? Suppose 6 numbers are there, so one number go from it, because we have already got that. So how many remaining numbers are there? You will have n minus 1 number. So from this 5 numbers, we have to choose the maximum element. So it will be 1 by n minus 1. Similarly, when that element is also chosen, how many numbers are left with us? 4, right? So for choosing the next maximum element, what will be our probability? It will be 1 by n minus 2. So if we consecutively keep on picking the maximum element for getting a random number, so the probability will stand out 1 by n into 1 by n minus 1 into 1 by n minus 2. And if you closely look at this, it will be 1 by n factorial. And if you keep n is equal to 10, it will be 1 by 10 factorial, which will come approximately 2.7 into 10 to the power minus 7, which will be very smaller number. It will 0.000000027. So we can assume it to be approximately equal to 0. So in total, this will bring our average time complexity of QuickSort to n log n. Now let's pivot to comparator. QuickSort is perfectly tuned for numbers. But what if we want to sort by some specific rules? So you can understand a comparator is a function that compares two values and returns a result indicating whether they are equal, less than, or greater than. So let's look at the language matrix. So in Java, Python, JS, C#, or Ruby, this comparator function will either return negative, 0, or positive. So when it will return 0, when the first element will come before the second element. And when will it return 0? When both the elements are equal. And when will it return a positive number? When the first element will come after the second element. Also, in some languages like C or C++, this comparator function will give the result true if first one comes before, and it will return false if the first one comes after. So in C++, it will return a boolean, and in Java, Python, JS, C#, and Ruby, it will return integer. And in C++, if you have to do ascending by sorting in the comparator, you will use first minus second, and similarly for descending, you will use second minus first. So let's see some problems on the same where we can apply the comparator. So let's tackle a problem 1 where you have to sort by factor. So basically two rules will be given. So you will be given an array. You have to sort it with respect to the count of factors. And the second rule will say if count of factors of two numbers is same, you have to sort based on their magnitude. So let's see the solution for the same with an example. So suppose your input is 9, 3, 10, 16, and 4. So how many factors 9 has? 3, right? It will be 1, 3, and 9, right? Similarly, 3 is a prime number, so it will have 2 factors. Similarly, 10 will have 4 factors, 1, 2, 5, and the number itself, right? Similarly, 16 will have 5 factors, and 4 will have 3 factors. So if you sort these numbers on the basis of the factors, so what it will be? It will be 3, 9, 4, 10, and 16. But the number 9 and number 4 both are having same number of factors. So when the number of factors of two numbers are same, then to solve the tiebreaker, we will consider the magnitude of the number. Since 4 is lesser than 9, we will keep 4 before 9. So our final sorted answer will be 3, 4, 9, 10, and 16. So let's see the code for the same. So you have one compare function which will take two inputs, int x and int y. So this function will count the number of factors which we have already learned in our initial classes. So fx will count the number of factors in the first number, and fy will count the number of factors in the second number. And if both the count is not equal, for ascending, we will return fx lesser than fy. And count of factors of both the numbers are same, then in that case, we will simply return on the basis of the magnitude. So in that case, we will return x is less than y. Now let's see our last problem of today, which is the largest number. So here you have been given some non-negative integers, and you have to get the largest possible concatenated number from the given input. So your array is 3, 30, 34, 5, and 9, and your output will be 9, 5, 3, 4, 3, 3, 0, because this will be the largest possible concatenated number from the given input array. So how will you solve this? So let's understand the code for this. So the function is function largest number, where a will be taken as the input, and now you will use the comparator function. So inside the comparator function, you have two elements, x and y, right? So your loop will run inside the comparator function, which is from x to y. Now for getting a number in the format xy, you will take the string representation of the same, and you will concatenate both the strings. So in this way, you will get both the strings xy and yx. So let's take this example only. So here you will get 3 and 30 as a result, right? So you will check 330, and next you will check 303. If xy is greater than yx, then x should come before y, right? So in our case, since 330 is greater than 303, so this will return 330 here. Now again, the next element will be 34. right? So we will again concatenate. Our xy will become 3, 3, 0, 3, 4, right? And our yx will become 3, 4, 3, 3, 0. So which one is bigger? This one, right? So it will return this. Now in the comparator function, we have two numbers which comes as 3, 4, 3, 3, 0 and 5. Again we will concatenate. Our xy will have 3, 4, 3, 3, 0 and 5. And our yx will have 5 and the second number is 3, 4, 3, 3, 0. So which one is bigger? Yx, right? So now it will return this number. So in the next iteration, our comparator will have 5, 3, 4, 3, 3, 0, comma 9. Now our xy will become 9, 5, 3, 4, 3, 3, 0 and our yx will become 5, 3, 3, 4, 3, 3, 0, 9. So which one will be bigger? This one, right? Xy will be bigger. And like this, we will get our answer array. After getting the sorted array using this custom comparator, we will initialize an empty string. We will iterate over our array and we will concatenate each number to our empty string using string builder. So why we are taking string builder? So that the space complexity remains at O of 1 only. But there is an edge case here. What if all the numbers are starting with 0? In that case, you have to return 0 or else you will return the answer. So what is the time complexity? Since inside the comparator function, we are running a for loop. So the time complexity there will be n, right? And since we are using the sort function and sorting will inbuilt take n log n. So in total, our time complexity will be O of n log n. N for executing the comparator function and n log n for sorting the numbers. And this will also give you the time complexity as O of n. So it will be O of n square log n plus O of n. So as we know, we will ignore the lower order coefficients. So this O of n will be ignored and our final time complexity will be O of n square log n. And since we are taking string builder to append the elements from the array into a string, so our space complexity will be O of 1 only. So this is a LeetCode problem. The link I have mentioned in the description as well. So to summarize the art of custom sorting, partition is the ON engine that drives the split, right? And QuickSort will leverage the probability for O of n log n speed. And finally, the comparators will swap out the less than operator, giving you total control over the rules of order. In the next lecture, we will learn about binary search on arrays. If you found this video helpful, please hit that like button and subscribe to Techmine Guru. Till we meet again, keep learning, keep coding, and keep optimizing.